organizers for inviting me to this meeting, which is very nice. It's my first time here in the Institute Principia, even though we're so close in Rio. But I am one of the fortunate people who was here before to the old IFT, which was a very pleasant place. So it's very nice to be back here in this complex here and now with this modern setting for conferences. So what I'm going to talk about today with you is what I'm calling hot and dense perturbative QCD. So it's similar in some fashion with what Alejandro was discussing, but I'm going to discuss the pressure and some observables and not the phase diagram, but parts of it in the presence of a very strong magnetic background. So this corresponds to work done together with Letícia Palhares, who is here, and Tulio Restrepo, who is in Houston. And it's being published in these two papers here. There's a follow-up paper that should appear soon on the coefficients of the expansion in mu over T in comparison to the lattice results at finite magnetic fields. So to motivate the discussion here, we can code several things, right? So it's in medium strong interactions under very string magnetic fields, so they're relevant for several things. So of course, for experimental setups, like in heavy ion collisions and the early universe and magnetars, these are the things that we can, in principle, observe or measure. They're also rich in new phenomenology, so there's a chiromagnetic effect, new phases of QCD, the phase diagram, some superconductivity that might appear, and so on. And last but not least, it's amenable to lattice simulation, so it's a new open channel for comparison, right? So it's model constraining from the lattice, can be tested for PQCD, and also non-perturbative methods. Well, this is all very nice, but unfortunately, life sometimes is more complicated, so that the real deal is up here. Of course, we want to compare with experiments, we want to see new phenomenology and so on, but here, it is very hard to theory, right? So it's difficult to compute with reasonable control over approximations and hypotheses. So fortunately, we won't end up very sad in this talk, because there's this part here, and here we can play. Right? At least we can play a little bit. I'm going to show you that's not the ideal situation, but it's getting better and better as time goes on, and people on the lattice can make this amazing developments and being able to compute at very, very hard, very large values of the magnetic field. And so it becomes amenable for comparisons with perturbative QCD, for instance, when provided lowest lambda level results and so on and so forth, we can directly compare to them reasonably well, as I'm going to try to convince you soon. So at very high magnetic fields, many interesting things might happen. So it was already shown like 10 years ago by our friend Andrade here, by his pioneer investigation of the behavior of the temperature. Not this is an old result from the Regensburg group for the T versus EB phase diagram, but Andrade was able to compute at much larger magnetic fields. I think it's 3.25 or something like this, GV squared. And then he found exciting lattice results for these values, extremely large B, and he was conjecturing on the a possible first order phase transition. Then there will be a critical point here. So many years afterwards, almost 10 years later, so the PISA group investigated and revisited this problem for much higher fields. So they were able to perform the simulations for 4 GV squared and even 9 GV squared, which is already pretty large. And then they actually found evidence for a first order line in the phase diagram. And then there must be a critical endpoint here. So nowadays we know there is at least one critical endpoint in the QCD phase diagram, which sits in the case of non-zero magnetic fields. Regarding the other one, T mu, we're still not sure, but regarding TB, there is evidence from the lattice that there is a critical endpoint besides the first order critical line. So that would maybe give us a hierarchy of scales of this sort, which is what we actually need to perform PQCD in a more or less reasonable and under control fashion, right? We need, as usual, temperatures much higher than the scales of the masses present in the setup. But also, since we want to restrain ourselves to the lowest lambda level, because life is a little simpler there, we wanted to have the magnetic scales much higher than the temperature. Right, so it's not quite yet on the lattice, but it's good enough already that we can play with that. Okay, so then besides lattice QCD, which would be the other tool that can provide predictions from the actual fundamental gauge theory, and that's perturbative QCD, right? So PQCD to order G squared in a non-perturbative magnetic background. So that was done many years ago for the first time, but we've revisited that much more recently. So the framework would be PQCD in a non-perturbative magnetic background. That means we have quark-gluon interactions up to order alpha s, so lowest order of correction, but we have the exact quark propagator in a constant and uniform magnetic field as was computed by Schwinger a long, long time ago. So that's the main idea. So the basic ingredients are here. So we have the exact thermal propagator computed by Schwinger in the 50s, and also rewritten by Chodos and company from MIT in this nicer fashion here that is very appropriate for doing loop calculations, right? So this is the kind of thing that we're going to use here. So a line here in this loop expansion for the fermions would look like something like this, and we're in the lowest Landau level approximation, then it's just first term in this series that will appear. So of course, we also need the gluonic part from usual hot PQCD if you're doing at finite T, and we need also these magnetically dressed quarks. So if you look at the diagrams here, the guy that is important here is this one, right? So this is easy to compute. There's a bunch of gluonic and ghosts and stuff that don't really matter here in terms of the magnetic field. This guy is the one that has to be computed. Two-loop diagram for very large B fields. So this is what I'm calling the exchange diagram here. And this has been addressed first in 2012, 2013. And what you can see is that in this limit of such large fields, when you go to the lowest Landau level approximation, this simplification happens, and this makes life way, way simpler. This 3+1 diagram here in finite temperature field theory becomes this two-dimensional diagram, exchange diagram here, with a massive gluon, so to speak. So massive in quotation marks. So I have an exchange contribution to the dimension 2 hot QCD with a massive gluon. And then you have a sort of average over this, what I'm calling this transverse mass of the gluons, which means that this guy, perp squared over 2QF B here, is this weight that is being used in averaging this guy here over all possible values of this transverse gluon mass. So as you can see, there's clear dimensional reduction, as was mentioned also by Alejandro a few minutes ago, in this quark dynamics. There are no UV divergences, so everything is finite here, which is nice. And because in D equals 1 plus 1, D equals 1 plus 1, the direct trace is proportional to the quark mass, there seems to be a trivial chiral limit. Now this also appeared in a few expressions in the previous presentation. So there's this proportionality to the square of the quark mass here. So that will lead to a trivial chiral limit, because when this is set to 0, this all vanishes, provided all these integrals here don't give some weird infrared divergence that kills this guy here, and there's something that remains. There isn't, right? So it's all well behaved, and so the infrared limit in the chiral limit is trivial. Okay, so we can show also that this next to leading order results are always 1 to 2 orders of magnitude below the leading contribution. So that might signal an improved convergence of the perturbative series in the case of a very high magnetic field. But that's to be seen, right? One has to go to high orders to show that this is the case or not. And as I mentioned before, there's a trivial chiral limit, so there's strong suppression for small masses, as was previously discussed too. So at the time, so 12 years ago, what we're saying is we computed the pressure with no running coupling, no running mass, no bands. We didn't look at any other observables, and we did no tests for ultra-high magnetic fields. So we revisited this about 10 years later, and now we included running coupling, running masses, bands for that. So we're measuring the kind of error that we have in the system that we are computing. We have the dependence on the choice of the randomization scale. I won't have time to discuss this in this talk here. And then we computed again the pressure with bands, the quark condensate that was computed on the lattice meanwhile, the strange quark number susceptibility that was also computed on the lattice meanwhile, and then we can do tests for ultra-high magnetic fields, which are sort of reached on the lattice. So as I said, this is what I wanted to have. It's not still at this level, but that's at least good enough to be more or less in the same ballpark, which is already a non-trivial. It's not obvious that would be in the same ballpark as the lattice results, but we happen to be there doing perturbative calculations. So just a technical thing here with what we had done before is that we had performed the sums first and then the integrals afterwards. It happened it's easier to do the other way around, so more recently we did the other way around. We performed the Matsubara sums at the end. This only valid for m equals 0. For m different from 0, you have to do the usual way, but then a few other things simplify, as you know. And then we can compute this next to linear order exchange contribution to the pressure, which looks something like this. Never mind about the details. You can read the papers or you can discuss in another time. Of course, we also needed leading order for quarks here, and we also need the gluons in the game. Okay, then we can compute the Chiral condensate. So the Chiral condensate is defined as this guy. Here's the derivative of the pressure with respect to the mass, and then we have a contribution from the free part and from the exchange diagram too. So for massless quarks, the true order parameter for the Chiral condensate, for the Chiral transition is this guy. Of course, we don't have massless quarks in reality, but so for light quarks, we have a pseudo order parameter given by the quark, the Chiral condensate. So this is, of course, an important observable, right? This can be computed on the lattice too. So, as I said before, the perturbative analysis is reliable only for very large T and even larger B in that hierarchy of scales that I mentioned before. So it cannot bring any information, no piece of information at all, near the phase transition or crossover. So we won't discuss anything close to the transition simply because it's not possible to do that using perturbative QCD. Nevertheless, there are these lattice results for high T and B, and so the comparison of the two first principle calculations is of course relevant. So from magnetic PQCD then, we can compute this derivative for the free term, and also for the exchange diagram we have nasty expressions like this, but that can be computed easily. Okay, on the lattice, one computes this F-flavor renormalized condensate to eliminate additive and multiplicative divergences, and this is defined by this difference here, whereas we are subtracting this 0B and 0T Chiral condensate. Again, to obtain the vacuum condensate, one cannot, here, in our case, take the zero field limit. It makes no sense here, because we're assuming from the start that B is super large. So afterwards, you can never do, well, let's look at the small field limit. This is nonsense, right? So I cannot address this. So we can also compute the strange quark number susceptibility, which is this guy here, the second derivative with respect to the strange chemical potential. And so given the presence of this derivative here with respect to the chemical potential, these pure vacuum terms are excluded. This is better for a comparison from perturbative QCD, since we cannot really access this magnetic vacuum sector of small b and so on. This is not available for us. Okay, so we also include running, as I mentioned. So alpha S is running like this. The strange quark mass is running like this. And these are the usual choices for the coefficients of the beta function, lambda ms bar for 2+1 flavors, and this guy who is fixing the running of the strange quark mass for 2+1 flavors too. So we're doing like thermal QCD in the presence of a very large magnetic field. So when you have no magnetic field, so besides quark masses, usually the only scale is temperature, which is assumed to be much larger than the quark masses. So the usual choice for the scale, for the running scale for everybody here, would be the lowest non-trivial Matsubara frequency, which is 2 pi t with a band around it. So it's usually taken between pi t and 4 pi t. It's usually a factor of half and a factor of 2, just to measure the spread of the error that you have in the perturbative calculation. In the present case, however, we had 3 mass scales, right? You have root EB, you have temperature, and you have the quark masses, right? So in the literature, you can find several different assumptions for the form of the running coupling. We think the most physical one, and the one that I'm going to discuss here, is this one. So that's a natural extension of what is done when you have T and mu B present in the picture, right? So that would be usually 2 pi T squared plus 2 mu squared here. And instead of that, we use EB as a natural extension. Okay, so then we have results for the pressure. So what I'm showing here is, if you can read here, you can read here, it's free pressure here. Then the exchange pressure contribution, right? We're doing this for the strange quark mass just because it varies more, so it's easier to see things. Then the ratio, which is sort of a measure of how perturbative calculations are doing, right? So it should be much smaller than 1. And then the full pressure here, the strange contribution. So as I just said, so this ratio here is a measure of the reliability of perturbation theory. It's more well behaved than in the case of no magnetic field. So if you play this game with no magnetic fields, the exchange diagram will make a big difference, right? It's not going to be nice and smooth like this. It's going to change signs of things, and then perturbative QCD behaves in a sick way, as you probably know. So you can go to ridiculously large B fields. Yeah, this is not found in magnetars or heavy ions. I don't care. I'm doing theory here. So I can just test theory going to ridiculously large magnetic fields just to see what happens. And if you look at the nice guys, they're behaving pretty well here for large magnetic fields. We can show also here the pressure for very large magnetic fields. Again, same kind of choice we had here. Free guy, exchange, ratio, and the full pressure for super high magnetic fields. Okay, then we can show the full pressure with bands, right? So the pressure is a function of the magnetic field for different values of the temperature, 300 MeV and 600 MeV. And you have the bands. The bands are kind of small here because the contributions coming from higher order are actually small. And again, this is increasing or decreasing the central normalization scale by a factor of 2, and this measuring the uncertainty. So again, this kind of purple case would be the one that I find the most physical. I'm not discussing in detail the rest, but one of them is fixed alpha S, and the others are different choices of the alpha S running sometimes to try to mimic inverse magnetic catalysis and so on. I don't care about inverse magnetic catalysis in this description here, so I'm just choosing the most physical one in my opinion. Right? So then we can look at results for the renormalized light Chiral condensate that has been computed on the lattice by the PISA group for 4 GeV squared and 9 GeV squared for EB values. So this guy is a function of temperature. And again, temperature is not large enough as we wanted it to be, we wished, and B is not large enough either. But still, if you look at the behavior, look at the purple band here, that would be our physical case. When you go to this kind of field to larger field, it becomes better. It's in the same ballpark as the lattice results, which is good news, right? So you can also look at the strange quark number susceptibility, and then we have results from the PISA group here again, and also from Androidi from ages ago, right, 10 years ago, I guess, for 3.25 GeV squared, and then 4, and then 9 here. And then again, you can compute the lattice results, which are still short for us. They're not coming to high enough temperatures and not large enough fields, but as you can see, it's in a good ballpark to compare to perturbative QCD. So they show the same qualitative behavior for different running choices, but here the quantitative behavior is actually very good from what we expected at first without seeing any of the results, especially because, as I said, many times already, this is not satisfied the way we would like it to be. So we can then move to the complementary case. So instead of finite temperature and 0 mu, we go to finite mu and 0 temperature, and then we can do the same thing. Then, of course, we don't have the benchmark of the lattice, but you can be brave and do it since we were in the same kind of ballpark when you compare that finite temperature. So then we are T equals 0, non-zero density. The sum integrals and distributions simplify, right? So you end up with something like this for the free part, as most of you should probably know. And the PF here is the Fermi momentum. There's a guy appearing here. This X is what is usually defined as square mass of the Fermi over 2QFB. And then we can compute also the lowest Landau level exchange contribution for finite mu, which looks like this. And then the hierarchy of scales that I would like to have would be this one. So the quark chemical potential much larger than the strange quark mass and much smaller than root EB, the analogous of what we had previously. And again, we're going to choose the running scale as root of square of 2 mf squared plus EB. So it's an extension of what is done in medium field theory. Okay. Then we can compute the pressure, and this is the result for the free pressure as a function of mu. Free, there's a band, right? There's a band because things are running, right? The mass is running, alpha S is running. So there's actually a band here, even in this case. And here is the contribution, the full contribution, the full pressure as a function of mu. So you can not really see this big kind of difference here. It's because there's no big kind of difference to be seen here. It doesn't change so much because, again, the exchange diagram is a small contribution, right? It's a correction of just a few %. And even for much smaller fields, like 10 to the 18 Gauss, possibly attainable in the core of magnetars, nobody really knows, right? So if you go close to the surface, it should be 10 to 15 or maybe 10 to 16. Nobody knows if this is going to be attained in the core of neutron stars, but in magnetars. But well, if it is, you can go down to this kind of value. And then the exchange contributions remain still quite small, right? So on the other hand, as I just said, the running effects are always relevant and also affect this leading term via the running of the mass, right? So this guy is getting this band because of the running of the mass. So since this is so, one can build a sort of PQCD-based simple analytic model where you just compute to leading order, but include running effects, and then you play with a sort of analytic expression, which would be this guy here, which is the kind of free case, including running. And then if you plot this guy here for smaller values of the field, so 10 to the 19 Gauss, I could do for 10 to the 18 Gauss, that would be a larger band here. Oh, thank you. Will be a larger band here. And you can look also at the ratio of the total pressure up to this order to the free pressure to see how it starts deviating from 1 here. So it's for small values of the quark chemical potential, right? So of course, we're pushing magnetic PQCD away from its region of validity. Everybody knows this. So this pressure should be matched onto a low density pressure if you want to try to address any phenomenology for magnetars. And this can be done. It's not done here, but can be done. And so what we can do here, just with the pressure and other values that we compute, in this case here from PQCD, is to constrain a few things in magnetars using PQCD at very large B. So for that, we need charged neutron systems as well as beta equilibrator matter. And so you impose the usual conditions for beta equilibrium and charge neutrality, and also have to have a density of electrons in this game. And then at the end of the day, you can compute the equation of state. Pressure is a function of the energy density, and you can compute mass radius diagrams. This is going like this just because it's pure quark matter. If you match onto some hadronic equation of state, it's going to do something like this, as usual. And here we compare it also to the back model to see what kind of difference appears. So this result should be valid for very high B. But then you can also compute observables or not observables, but theoretical constructs such as this ones. So the mass as a function of B, normalized by 10 to the 19 Gauss, or the radius of the star also as a function of B. And then you have these cones here, or these bands here. So if you have a model and you compute your magnetars with your preferred model, when you go to very large fields, they'd better enter this here. So it's the same kind of thing that we've done like 11 years ago for the equation of state for finite density QCD, or finite density neutron star matter. So when you have a cone coming from perturbative QCD as you go down in mu baryon, for instance, and a cone going up from effective field theory, and then any equation of state that you build from your preferred model would rather enter this, or you're being consistent with the equation of state and high density. So again, PQCD, even if it is not approaching the physical region, can still constrain any model that you build, provided that you enter this kind of cone as you go to very high values of the magnetic field in your preferred model. So that brings me to my final remarks, which I think was more or less in time. So first thing is that the magnetic thermal or dense PQCD with physical quark masses indicates that these loop corrections are subdominant in the pressure for large values of the magnetic field. So the NLO term is comparatively very small, usually a few percent corrections. As I said many times, the window of applicability is still very narrow, but the results obtained from a clean first principle calculation that can be systematically improved and controlled. So results for the Chiral condensate and strange quark number susceptibility were compared to recent lattice data, away from the Chiral transition, of course. Even it's still out of the region of validity, PQCD results seem to be in the same ballpark, which is encouraging. I would say it's actually remarkable. We did not expect it from the outset. It would be great to have lattice results at even higher B and also temperature. Higher temperature would be very nice for us to compare. And of course, for huge values of B, one can build a PQCD-inspired analytic model in the case of cold and dense PQCD. That might be relevant for magnetars microphysics, and it can be used, as I said, to constrain models if you use this cone and you demand that models enter this cone. And with that, I'll finish, and thank you for your attention.
Who first?
Okay, I have a very simple question regarding your exchange diagram. I don't think it matters quantitatively at the end of the day, but when you are calculating, and I'm all 100% for dimensional reduction, as you may know, but in that particular case, when you're using it, I think you cannot use it because, in fact, you're actually throwing away the divergences of that exchange diagram, which you would only see if you actually sum up over all Landau levels. By restricting to 1+1 dimension, you are kind of throwing it away by hand, and I'm wondering if that is going to dramatically change your final conclusions.
Yeah, I know that you cannot do this when you're computing the energies and so on, and when you try to do like one look of computations of the energies, you go to the lowest Landau level, throw the baby with the water. Yep. I don't think we're doing the same thing here for the exchange, but we can discuss. One thing that we want to do is to include at least one more Landau level to be able to push to smaller magnetic fields.
That wouldn't help because you need the infinite sum of Landau levels.
If there is a problem,
to capture
yeah. If you're computing the dispersion relation and things like that, and you do like this, I know you're throwing the baby with the water, but I don't think we're doing the same kind of mistake here.
Okay.
Yeah, I know what you mean. Yes. And it's been wrong in many places. Yes.
Hi, Eduardo. Can you come back to the slide before that one with the mass against radio?
Right.
This one, yeah.
Okay.
I have two small questions. The first one is you doing a theoretical talk.
Yes.
Including early universe, the magnetic field is far from the phenomenology, right? These values.
Say it again?
If in the early universe you have huge magnetic fields.
Yes.
But this is much more higher, right?
Yeah.
Okay.
Yes.
Second question is, when you do this PQCD approach, you need to obey a hierarchy of scales.
Yes.
The magnetic field square root needs to be larger than the chemical potential.
Yes.
So I do not understand the right-hand plot because it's 0.1 GV squared 10 to 19 Gauss. And you have chemical potential around.
I'm pushing beyond the region of validity. Yes.
You are not obeying that hierarchy of scales in the
Yeah. If you go all the way down, yes. Yes, exactly. I have to go up there to keep it.
Because that thing that you need to match to PQCD is already for high densities, right?
Yes.
Much more than the phenomenological point of view.
Yes.
Right?
Yes, absolutely. But you still must. Yes.
Yeah. Thank you.
Hi. So hi, Eduardo. So I just want to ask you the question about the pressure. I mean, so for this application to the magnetic, the neutron star and the quark star, did you also include the magnetic field pressure? And related to that, so the pressure distribution could be.
It is there. It is there. It is included.
It is included.
Yes.
The
When I'm
magnetic
plotting
field squared.
I'm plotting the full thing, yes, it is included.
Then related to that, then depending on the scheme, either you keep the magnetic field, the magnetic flux, anyway, the pressure
Actually,
distribution could be isotropic or the anisotropic. Yeah, right.
Yeah,
So
yeah. No, I
yeah.
should do.
Yeah, so
I should
that is actually the
anisotropic here.
picture, yes, developed by
Yeah,
Gavin.
yeah.
In fact, so in this case, is this really that total pressure
No,
isotropic? Or
I'm ignoring
you
the
ignore?
asymmetry. I'm not doing magnetars here because I'm ignoring this. I should take into account the asymmetry, for sure.
Yeah.
The asymmetry is going to be even very large in the case of magnetars, and one must
Yeah.
include this when we're doing phenomenology,
Yeah.
right? This is
Okay.
just one piece, so this is log Z, right?
Okay.
Yeah.
Okay. Good. Thank you.
More questions? I don't see more questions. So let us thank Eduardo again.
Thank you. Sim.
Thank the organizers for this nice workshop and the invitation to talk. So I'm starting 15 minutes late, right? 10. Okay, fine. So what is the motivation of my talk? Is that time dependence is a common feature of strongly interacting phenomena in the early universe, and magnetars and heavy ion collisions. So the quark condensate is the quantity that I'm going to focus on, and is affected by temperature, by density, and strong magnetic fields. And everybody knows that. If not, they should. Time scales of the condensate dynamics are important for hadron production, for example, heavy ion collisions. So the question is, how is the quark condensate affected, or the time dependence of these effects are important in these settings. So here I will show that a couple of studies of the non-equilibrium time evolution of the quark condensate, first for very strong magnetic fields, and also another computation when I don't have magnetic fields, but I have the possibility of forming inhomogeneous chiral condensates. So what is the typical situation I'm looking here? Is that a system that is, say, in equilibrium is forced to change to another out of equilibrium phase. Okay, you can do it suddenly or slowly. Okay, I'm going to consider what is known as the quench, that is a quick change of the state. So the evolution goes through spatial fluctuations that take the system that usually is homogeneous and goes through a sequence of highly non-equilibrium homogeneous states. So how to compute these things? Okay, so it's difficult, up to now it's very difficult to describe, or even impossible to describe the system using quarks and gluons, the microscopic degrees of freedom. Okay, so how you approach this problem? You focus on a small number of semi-macroscopic variables, and in this context they are known as the order parameters, densities. Okay, scalar densities, vector densities, so the scalar densities that they might serve as order parameters for this phase change. Yeah. There is a hypothesis there that the dynamics of phi is lower than that of the microscopic degrees of freedom. So then this is the framework of the Ginzburg-Landau type of equations. The name Langevin is there when you include fluctuations. So if you don't include fluctuations, thermal or fluctuation, for example, then you are the normal Ginzburg-Landau framework. So how you describe the evolution of these order parameters, okay? You have a free energy, okay? Suppose, just for as an example, you have here, say, a gradient, okay, a spatial gradient, and here's the potential. R can be positive or negative, and this is always positive, okay? So then, suppose at some instant of time, you have an equilibrium state where the order parameter is equal to 0. Think about the Ising model. The Ising model, okay, at very high temperatures, the magnetization is 0. Magnetization here in this context is phi, is the order parameter, okay? So it's sitting down there at this minimum of this potential, okay? And how you find it is just minimizing this free energy, okay? Now, suppose you change suddenly that R parameter. It was positive, that's the reason is a single well, and then you change it to negative suddenly. For example, changing the temperature in the Ising model, okay? Change the temperature below the critical temperature, and then it develops 2 minima, okay? But this is so quick that the system is still sitting there at 0 there, and the order parameter is equal, the system is still sitting there. This is not working. It's here. Okay, fine. All right, so how you describe that? So this then Landau proposed, we are very close to equilibrium, okay? This is like a mechanical equation that you then, this will be pure equilibrium equal to 0, but then you postulate now this acquires a time dependence, and then the equation that describes the rolling down of this, the order parameter to this minimum or to that minimum, okay, is described by that first order equation. But here we are neglecting then fluctuations. Okay, it's just rolling down in one direction or the other direction. Okay, so but we have thermodynamics there. This is still at finite temperature. So then you have to include also fluctuations. Okay. As I said, it's purely diffusion, no thermal fluctuations. Fine. So you can put simply a noise field there by hand, and this people have done many years, okay? And to respect fluctuation and dissipation theorem, this noise field, it depends on this eta parameter that is there, okay? And then now you have fluctuations, and then you have a more realistic description of this dynamics. So eta is dependent on temperature in general, okay? If you have magnetic fields, density also depends on that parameters. So it depends on the microscopic dynamics of the system, okay? So just to give you a picture, what can we expect? So this is an initial distribution of the order parameter or the magnetization, okay? On average, you have equal numbers of spins pointing up or pointing down, and so the average is 0. But then as time increases, then part of the system falls to one of the minimum, and the other part falls the other. You have domains. One is say +1, -1, and so on. So eventually, after some long time, this will go to will settle down in one minimum, for example. Okay. Great. So this is what we expect. And this now enters the different universality classes, like when we have equilibrium, okay? We have different universality classes, and the same we have here. Here's much simpler. Here's A, B, C, D, F, G, H universality classes, okay? Model A is when we have a non-conserved order parameter like the chiral condensate, or the magnetization, and things like that. Model B is when you have conserved order parameters. Say baryon density is something is conserved. The equation is not the one that I have shown, it's different. It's the Cahn-Hilliard equation, and so on and so forth. Okay? Fine. So how can I derive such an equation? Okay, that I have shown the Ginsburg-Landau-Langevin equation. I have a microscopic theory, say in this case it's not so microscopic, but it's the linear sigma model. Okay, and I want now to derive such an equation for the time dependence of the chiral condensate in the presence of a magnetic field. Okay. So then I have here the thing. The parameters are chosen such that I have a crossover at equilibrium. Okay. And now I couple a magnetic field, and how can I compute from there the time dependence of the condensate? The condensate here is represented by the sigma field. Okay. The usual quark condensate. So I will, this example that I'm going to show is for parameters that are typical of a heavy ion collision. Okay. So I will also consider very close to equilibrium. Okay. That is probably, or most certainly not what happens in a heavy ion, but it's kind of like hydrodynamics, where we suppose we have some kind of local equilibrium, okay? And I will make perturbation around the equilibrium of distribution of the condensate, okay? So what is the source of that eta parameter? That eta that appears there in that equation, okay? That describes dissipation, okay? So is the sigma field decaying in quark, anti-quark in this case? It can decay also in pions, okay? So these are the source of dissipation in this kind of model, okay? And then I want to see what are the changes that I can expect when I have strong B. Strong B here means lowest Landau level approximation, okay? And I want to have an analytical understand as far as I can. So how I do that? This is an old subject, okay? Is how to derive this kind of equation through in quantum field theory, non-equilibrium quantum field theory, okay? So this is known as the Schwinger-Keldysh formalism. Okay, you have to duplicate your degrees of freedom. You have to contribute. You have to consider this coming from minus infinity, plus infinity, going back. So you have to replicate, duplicate your degrees of freedom there. Okay. So such a calculation was done by many people in the absence of magnetic field. Okay, so this calculation then is done in the presence of a magnetic field, a strong magnetic field. Okay, it's very difficult to solve the equation. Sorry, it's very difficult to solve the equation of that arises when I have to find the stationary points of the effective action. Okay, so I get the equation of motion, and that is very difficult to solve. So what you do, you expand it around equilibrium. Okay, so this is the quark propagator in the presence of a magnetic field. Okay, this SAB, AB, so plus plus is the upper branch, and minus minus the other, and the other are the vertical thing. So what I do, so I have, say, an equilibrium distribution, and these are the fluctuations, okay? And the same for the quark propagator, okay? And then I get an equation for the thermomagnetic equilibrium part that I can solve. Okay? And now I'm going to neglect pions. I can include it. It's not a big deal. It's just to show you here how it goes. Okay? And the equation of motion for sigma now is complicated. Why? Because I get an imaginary part because of this decay process. So strictly speaking, the effective action doesn't have a stationary point, okay? Because it is complex. And then what you do? Then you use what is called this Feynman-Vernon trick, that you replace the imaginary part by fluctuating fields, okay? And that is where the noise enters, okay? Is when you, I don't have time for that. I already talked for more than 10 minutes, okay? So I cannot explain all that, but it's a very simple idea, okay? You simply take the imaginary part, exponentiate it, and then re-express that the exponential as a path integral over fluctuating fields. At the end of the day, then you get, you see, you have a second order derivative here, and you have this derivative here, and other stuff here, and here's this noise field, okay? So if you want to see these details, you have dissipation kernel, you have colored noise in general, and it is still extremely complicated, okay? Now then enters the first approximation regarding the quark propagator. What you do, use the lowest Landau approximation, and then you have that equilibrium part known, okay? And then you can go to momentum space, and then you get this expression here. There is an approximation down here that I didn't mention, is how you treat memory, okay? How you treat memory, you suppose you are at time t. What happens there? You suppose that are harmonic behavior. Then you can integrate from minus infinite to the time that you are, okay? This is called the harmonic approximation by the Frankfurt group, and then you get this momentum space equation. When eta is equal to 0, this is nothing else than the classical equation of motion that describes simply equilibrium, for example, and some time evolution, purely non-fluctuating and not dissipative, okay? Fine. Okay, this is just equilibrium, saying that I can reproduce all results in equilibrium, and this is the important part, okay? And when you have only temperature in the game, the eta is like that. Eta controls the complete non-equilibrium and the fluctuation in the system. It comes from sigma going to a quark-quark in this case here. There's also pi-pi, but this graph has only quark-quark, okay? Then you see there is a kind of a huge change here in the behavior of this eta, okay? So then this signals that we can expect big changes in the dynamics of the evolution of the quark propagator, of the quark condensate, okay? So this expression was known already there. I think I gave the reference before. This is purely temperature dependent. Now, if you have the magnetic field there, this is changed to that. You see here the dimensional reduction, and all that is there. Okay. Of course, you cannot get this from here, putting b equal to 0, because this is the lowest Landau level approximation. Okay, it's only valid for high values of b. Fine, so this is then the change in this eta, okay? And why is it so different? Okay, it's so different because the quark mass, the sigma mass, all those play a role here. You see m sigma, m quark. They change with temperature and the magnetic field. You have magnetic catalysis in this model, so you have the quark masses increases and sigma mass changes and all that. So then you have a different behavior of dissipation and fluctuations. Okay? This is just to explain what I just said, okay? And now I'm going to solve this equation. Okay, I'm going to solve first for a very short time. So I imagine that I have this system at, say, at 0, and then I will run it to for long times and short times. Okay, at short times I can solve the equation analytically. Okay, and I get this thing here. Okay. And what I learn here is the following. For different magnetic fields, I see how the field grows, okay? So here is for the weakest field, and so it grows very fast. You imagine this double well, you have the system sitting there, okay? So the tendencies at short times is just to roll down very quickly. Rolling down means what? Sigma increases. And this is what I show here. Okay? But as the magnetic field increases, so what happens? The dynamics slows down. Okay? Because of that eta parameter there. Okay? Then you see how it behaves, and has also some momentum dependence. That is not so relevant, but here is, say, for the present estimate, as I said, I'm using parameters of the sigma relevant for a crossover and temperatures and magnetic fields of people think are relevant for heavy ion collisions. Okay, I don't change the magnetic field during time evolution. I keep it fixed. Okay, and then I see that I can have delays of 1 Fermi over, say, the difference essentially from this one to this one. I get a considerable delay of the condensate starting from 0 to acquiring some finite value. Okay. Now I have a long time. Now I solve it for long times. I have still 5 minutes, okay? Okay, good. Yeah, thank you. Plus the 10 that I had before, okay. So this is what I'm saying here. At short times, I have this explosion, okay, because it starts rolling down of that double well, okay? And then the condensate starts bouncing back between the two minima, and eventually it will settle down. But what is the time scale here? You see around 10, about 10 Fermi over C. This has not thermalized yet, has not reached the equilibrium, okay? And 10 Fermi is more or less what we think is the duration of the expansion of a heavy ion. Of the QGP. Now, for this case, okay, the previous one I had 20, and the temperature was 100 MeV. Okay, I started, say, from a very high temperature, okay, where the quark condensate was 0, and then I lowered the temperature to 100 MeV. Okay, and that has not yet reached at the value of the condensate that I expect at that value of temperature. Now, if I drop the temperature, I quench the system to 50 MeV, then it seems it has more or less thermalized. Thermalized, what I mean is it settles down to its value that I expect at equilibrium. Okay? As I said, I don't have B dependent, T dependence on the field. Okay, but this gives me an idea how to expect and how I can. Now, the last 10 minutes I have, I will discuss the same framework, the same setting, okay, but at finite density. And here I'm concentrated not on the effect of the magnetic field, but of, I'm interested on that inhomogeneous phases. People have computed, say using models, have shown, have proved that actually the ground state or the equilibrium state of a dense, say low temperature, high density is not homogeneous. The quark condensate is not homogeneous, has some inhomogeneous feature in space, okay? It's extremely model dependent, all this stuff, okay? And for one dimension, say, you have kinks and other things, okay? D equal 2, you have these kinds of crystal, and D equal the domain wall networks, and so on. And there's an entire different kinds of inhomogeneous behaviors that people have found, NJL model and Gross-Neveu and sigma, linear sigma, and so on and so forth. Okay? So the point here I want to make, never mind if they don't exist actually. Suppose this eventually in QCD is proven that we don't have these equilibrium non-homogeneous condensates. Okay? We can still see, and it might have physical effects during the time evolution. Okay, because if you, as I said at the beginning, I have a system in equilibrium, homogeneous, say, and it goes to another phase. During this path to the new equilibrium states, you form these domains, okay, of different values of the condensate, like that picture of the Ising model that I have shown. So then this is what we want to show, and for that we use a model, okay? So the early work I did here was with Juan Pablo Carlomagno, okay? And this was when we did not consider fluctuations, and it was only done in one dimension. So here, this is work with Theo Mota, which is a postdoc there at the IFT, here at the IFT. And so now we included fluctuations and went to 3 dimensions. Okay? Fine. So this is then in the context of this model, is a Nambu-Jonah-Lazino model with a extension, say. It's called the non-local NJL model. And this little g that appears here is the Fourier transform of that capital G there, okay? The nice thing here, I can calculate a Ginzburg-Landau-Langevin equation from this model, okay? So what I'm doing is the following. So the phase diagram is given by this, okay? But I'm quenching from here, where the condensate is 0, to here to a value that is non-zero, but the stable, the equilibrium state is homogeneous, okay? It is homogeneous. It's not inside here. So the non-homogeneous phase that people find is in this, between these 2 spinoidals, okay? So what is the intent? Time is over, right? 2 minutes. And then, just to say, I'm quenching this. The system was here, okay? And I brought it suddenly to this point. The equilibrium solution of the condensate is homogeneous. So what we find? In one dimension, this is the initial condition, okay? Is the initial condition, is bouncing around 0, okay? And then time. Here is time, it evolves and settles down to that. So this is one noise realization, for one realization of that noise field that I have. Now I restart my random number generator, okay, and I already see at short times here a configuration like that, but at higher times it goes to that value of sigma, okay? I redo the calculation now with a new family of random number generators such that satisfies that expectation value, and what I find, a kink, which is one of the equilibrium solutions when it's inside of that thing here. So if I run it for longer times, longer times, this settles down to homogeneous. But for these time scales here, that is more or less of the order of heavy ion collision duration time, okay, I have a kink, double kink, and so on. The equilibrium solutions are just flat, okay, zero. Equilibrium to one of the minimum, minus 200, the left of the minimum, and here's the right. 2 dimensions. So what I see, okay, very long times, there are some, so this is one family of noise realization, another family of noise realization, another family of noise realizations. Okay, so depending on how this evolves during time, I can get at long times is still some non-homogeneous chiral condensate. Okay, but for others, it settles down to one of the minimum, for example. Okay, so I have, this reminds me of a kink here, a kink in, so it's like a big kink, uniform in one direction, but in that direction, okay? 3 dimensions, okay? Again, this is a typical configuration, okay? Time runs here, okay? Runs here. So I start with a completely mixed, close to 0, and then you start seeing the separation here of the phases. Eventually, you see such things like that. Okay? So the equilibrium solutions, if I let it run for 1 day, 2 days, eventually this will be all flat. Okay? Because the parameters, the temperature, and the density are in a region of the phase diagram where the condensate should be homogeneous. But in the meantime, it has all these bumps and different configurations. Okay? Fine. Since Anna is getting nervous, let's focus in this line. So the dense matter case, the patches of non-homogeneous condensates, although not strictly stable, have remarkably long lifetimes. And this, why this might be of importance? Because of these neutron stars, mergers, okay, that gravitational waves can see some effect, okay? This is the maximum frequency of this gravitational wave, that there is an empirical relation between this frequency and the deformability lambda. In the presence of this non-homogeneous, that changes. Okay, this empirical relation might not be, or will be some effect. Okay, so gravitational waves might be able to detect these features of that thing because they live very long. Okay. Thank you.
Time for one quick question. We can ask other questions during the discussion.
Yeah. Is this different physically from what were called the disoriented chiral condensates? Which people look to death.
This, the idea is very similar, right? Because also there you found patches of different values of the condensate, but the signal, I think, was is a bit different, the decay of this thing. But the formation, I think, is more or less similar to that.